dear students, welcome to Easy BTech, your guide for BTech and beyond. And we are going to see subject signals and systems. And today's topic properties of LTI system or LTI systems. So this channel is very helpful to you. All subject videos are available in this channel. So all of you subscribe, share the channel. Let's start our session. Properties of LTI system. So in the previous session already we discussed some properties like commutative property, associative property, distributive property, step response. All those we discussed. Now we are going to see continuation of previous session. Still we have some more properties. So in the previous session step response we discussed. Step response. What is step response? What is the meaning of step response? The response of the LTI system. This is the LTI system. Response means output. So generally LTI system input is x of t and its impulse response h of t. Output is y of t. So to get the output, how to get output? X of t convolution h of t. So convolution is very important to see the output of linear system. So this is the convolution, right? So convolution is useful to find the output of the LTI or linear system. So now step response. So in the place of input signal we are going to give unit step function or unit step signal. So whatever the output is coming, that will be called as step response. So how to write step response? So we indicate step response s of t. So this is the indication of step response. So in the place of input, unit step signal, convolution, impulse response h of t. So if you write convolution, that means integral minus infinite plus infinite. So we can also write like h of tau, u of t minus tau d tau. U of t minus tau d tau. So already we discussed about u of t minus tau. It is the left sided signal. So I am plotting it. And this is available up to t, small t, and it is 1. So this is the u of t minus tau. Already we discussed how it is plotted. Already we know. So that is why I am drawing directly. So u of t minus tau is 1 up to t, from minus infinite to t. Therefore the limits in the integration minus infinite to t h of tau and u of t minus tau is 1, that is why h of tau d tau. So if you observe the relation, this relation, if you observe carefully, what this relation is saying, step response is equal to integration of impulse response, right or not? What it is saying, step response is equal to integration of impulse response. So this statement we can also say like, so this is the point here, please remember all of you. So step response is equal to integration of impulse response, or we can say impulse response equal to d by dt of differentiation of step response. So both are same meaning. So impulse response h of t is equal to d by dt of step response. So very important point here. Right? Clear or not? Impulse response and step response relation. Let's go to another property. Shift property, time shift property or delay property. Time shift or delay property. So what is the delay property? We discuss now. What is the meaning of delay property? So if you take LTI system, the output is y of t, input is x of t, and impulse response h of t. X of t, h of t, output y of t. So output expression y of t is equal to x of t convolution h of t, x of t convolution h of t. Now delay property means if input is, for example, x of t minus t naught, time delay, or it is shifted, then what is the output in this case? The same LTI system, its impulse response h of t. So what will be the output now? So that is a time shift property. So your output is delayed by same amount. So y of t minus t naught, y of t minus t naught. So if you see the proof is very easy. So convolution we know first. We take convolution. So y of t is equal to x of t convolution h of t. So convolution integral minus infinite plus infinite x of tau h of t minus tau d tau. Or also we can take like this, integral minus infinite plus infinite h of tau x of t minus tau d tau. Okay. So now I am going to write this second statement. What is the second statement? X of t minus t naught convolution h of t. So what will be? This must be equal to y of t minus t naught. That we are going to prove. So take convolution of x of t minus t naught convolution h of t. So consider this. Now how to write this? Same integral minus infinite plus infinite. We can also take like here x of tau. So here x of tau minus t naught. Just t is tau. So same thing I am doing. H of t minus tau. So take h of t minus tau d tau. Okay. Now consider this x of t minus t naught. Sorry, tau minus t naught. Let tau minus t naught is equal to p. I am taking tau minus t naught is p. By this tau will become p plus t naught. So t naught is a time shift. Next dt will become dp because t naught is constant. And what about limits, lower and upper limits? So tau lower limit minus infinity. So minus infinity minus t naught. So lower limit is minus infinity is equal to p. Upper limit plus infinity is equal to p. So limits are not changing. Okay. So all these we are going to substitute in this integral. Then we can see changes. The all we are going to substitute in this integral. So let's take that integral. Integral minus infinite plus infinite x of p, right or not? Because tau minus t naught is p into h of here tau minus t naught is equal to p. Tau is equal to p plus t naught. So t minus tau. Tau is what? P plus t naught. So minus p minus t naught. Right or not? And d tau is dp. So dp. In the place of d tau we are taking dp. So this integral just I am slightly modifying, rewriting x of t into h of t minus t naught minus p dp. So if you compare the integral what we have now with y of t, so this is y of t. So just do comparison, we can understand the result. We can understand the result. Just do comparison of these two. So here tau, here p. no problem. Tau is a dummy variable, here p also a dummy variable. So here we have h of t minus tau. So here it is y of t. But in the place of here t, we have t minus t naught, h of t minus t naught. So this total integral will become y of t minus t naught. So this is the answer, y of t minus t naught. Very simple. Okay, from convolution integral only we can prove it, y of t minus t naught. So this is the result. Similarly, here x of t minus t1, the input signal is delayed by t1 and impulse response also delayed by t2. This is the case now. X of t minus t1 convolution h of t minus t2. What is the output? So output y will become t minus t1 minus t2, y of t minus t1 minus t2. Okay, so input is coming late by t1, impulse response is late by t2, then output also late by t1 t2 minus t1 minus t2, or also you can write, so I am writing here x of t minus t1 convolution h of t minus t2 will become y of t minus t1 plus t2. So output also delayed, output also shifted or delayed. So this is a time shift or delay property. Very simple. Okay, right or not? Next, go to another property, duration property. Duration property. Duration property. So this I can tell simply. Suppose the input signal x of t is available from t1 to t2. Its duration is t1 to t2, or the signal is available from t1 to t2. This is the input signal. And impulse response h of t. Impulse response h of t. Impulse response h of t. This is available from, for example, t3 to t4. Now what is the duration of output? That is the meaning of duration property. So output will be available where to where. So what are the limits of output? These are the limits of input t1 to t2 and the impulse response t3 to t4, duration or limits. Then output is, so add lower limits of x of t and impulse response, that is t1 plus t3 plus t3 less than t, upper limits also add, so t2 plus t4. So this is the duration property. The input signal, impulse response, lower limits added, that will be lower limit of output. This is the lower limit of output, and upper limit is upper limits of x of t and h of t, t2 plus t4. This will be upper limit of output y of t. This is the duration property. Okay. Next, one more we discuss, convolution with impulse or unit impulse. Convolution with unit impulse. Convolution with unit impulse. Del of t. Unit impulse means del of t. So if you take the signal x of t, convolution of a signal x of t with del of t, that we are discussing. Convolution with unit impulse means, so consider x of t, you just consider x of t, convolution del of t. What is the result? X of t convolution del of t. So how much? The same signal x of t. Shifted impulse, I am taking now shifted impulse. Shifted impulse. That means x of t convolution del of t minus t naught. So impulse is shifted now. So what is the result for this? X of t convolution del of t is x of t. X of t convolution del of t minus t naught. So the answer is x of t minus t naught. Shifted signal we get. Okay. Just see this proof. So we know convolution formula. What is the convolution formula? Integral minus infinite plus infinite x of tau del of t minus tau, del of t minus tau d tau. So if you take del of t minus tau, del of t minus tau, what it means? Impulse. Del of t minus tau means it is the impulse at tau is equal to t, the location or place at tau is equal to t. So you take that tau is equal to t and substitute this tau is equal to t in this x of t, because we have multiplication. That I am going to do. Multiplication means see the location of impulse, that location is substituting in next function or x of tau. So what we get? What we get? X of t, tau is equal to t, so x of t I can write outside the integral, and integral minus infinite plus infinite del of t minus tau d tau. So this integral represents area under impulse. This integral is area under impulse, which is equal to 1. Area under impulse is 1. So 1 into x of t, answer is x of t. That's all. Right or not? In the same way, we get x of t convolution del of t minus t naught is equal to x of t minus t naught. So very, very important. Convolution with the unit impulse. Okay. And next thing we are going to see causality and stability. Very, very important. Very, very important property. Causality and stability. Very, very important. So for causality, the condition is a continuous time system is causal, or it is causal system if its impulse response, that is h of t, is equal to 0 for t less than 0. This is the causality condition. The impulse response is 0 for t less than 0. Left side, there should not be any impulse response. H of t should be 0. That will become causal or causality condition this is. So this is the causality condition. Now stability. What is stability? So see stability condition. If the impulse response of the system is absolutely integrable, that means integral minus infinite plus infinite mod h of tau d tau, if this value is less than infinity, the impulse response integration is less than infinity. Less than infinity means finite. It should be finite. Then system is stable. System is stable system. System is stable. See how this condition, why this condition we can see. So generally if you take LTI system, consider LTI system with input, output and impulse response. So input is x of t, its impulse response is h of t, output is y of t. So the output is equal to convolution of input with its impulse response, that is x of t convolution h of t, which is equal to integral minus infinite plus infinite, integral minus infinite plus infinite, x of tau h of t minus tau d tau, or we can write like integral minus infinite plus infinite h of tau x of t minus tau d tau. Now if input is bounded input, limited input or bounded, the input is bounded input, then output obtained y of t is also bounded output. Output is also bounded. Then this system is called Bibot stable, bounded input, bounded output, stable system. Input is bounded input, output is bounded output. So let's take the input value, bounded input value. So let's take it is mx, the value of input. Magnitude of input is, I am taking mx. Consider it maybe 10 or 20 or something, mx. So I am going to see output now. So output must be bounded output like my, maybe 30 or 40, some finite value output must be bounded. So go with this condition, then output y is equal to, so in the place of input I am using this integral, we can take mx, that mx I am writing outside, and integral minus infinite plus infinite h of tau d tau, h of tau d tau. So the value of y of t must be bounded, then only system will become stable, right or not? Y of t so must be bounded. So to get the y of t bounded, already input is bounded, input is in limits, it is finite, input is finite already. So who will decide y of t is bounded? This integral will decide. Integral minus infinite plus infinite h of tau d tau will decide. Therefore the system become bounded stable, or it will be stable if the its integral value h of tau d tau, this integral is less than infinity. Here I written condition. So integral minus infinite plus infinite h of tau d tau is less than infinity, then the overall y of t will be less than infinity or bounded or finite. This is the clarity, stability. Understand? So to become y of t, the value of y of t is less than infinity, like my, to get y of t my, what is the condition? When this become less than infinity, this integral will decide. So integral minus infinite plus infinite magnitude of h of tau d tau must be less than infinity, must be less than infinity, means finite, so that our y of t also finite. Then the system is called Bibot stable or stable system. So very important this condition. To check the system is stable or not, its impulse response integration is less than infinity, means absolutely integrable. H of t must be absolutely integrable. Okay, so these are all properties of LTI systems. Okay, so thank you students, thank you. Watch videos regularly. We meet again, we discuss another topic in the next session.